find your top one. There. Okay, there's our balloon right
Hey,
there.
I want to blow it. I want to blow it.
Yeah, it's got some liquid in it still there. Okay, now look what's happening there. What's happening? Blow on it.
I want to blow it. I want to blow it. I'll blow it.
Blow that first part there. So, what happened to the balloon? It expanded, right. It did what at first, though? It contracted or condensed, right, it shrank. And then it expanded. So the air inside of it, right now, is filling it all up. Now, if the air stayed the way it was, could the balloon have shrunk down? No, right, because the air is what's holding it in this shape, right? So the air froze, too. You're right, the air froze inside as well. So what do we breathe out? Carbon dioxide, right, a lot of carbon dioxide. And when you freeze carbon dioxide, do you know what you get?
Dry ice.
I bet most of you have heard of it.
Dry ice.
Dry ice. Yeah, I knew you would know. Yeah, it's called dry ice. Dry ice is frozen carbon dioxide. Now, you guys know, has anybody never seen dry ice? Some of you haven't? Yeah, somebody probably hasn't, right? So, those of you who have seen it, what does it look like?
Ice.
It looks white. Yeah, yeah. It just looks like little chunks of white. So, inside this balloon right now, we're freezing the carbon dioxide that I blew inside there. And so what we'll get is little chunks, where's my coat? We'll get little chunks of dry ice from inside the balloon. So we're going to let all that air freeze up inside there, then we're going to cut the balloon open and we're going to see what my frozen breath looks like. You guys are holding your breath in anticipation right now, and I'm about to be holding my breath literally. There we go. All right. You guys see all that? Whoops. Still some out there. Okay. So all the white stuff you see in there is the frozen carbon dioxide that I breathed into the balloon. Yeah. You guys see that? Can you guys see it back there spinning around in the glass? Yeah. Okay. Okay, so why am I spinning it? See my nose? I'm doing that on purpose. It doesn't just spin by itself.
It'll stick to the glass.
So well, it's already solid. It's frozen.
So you can see it better?
Partially so you can see it better, yeah. The main reason is, though, because dry ice is very, very cold. Not as cold as liquid nitrogen, but it's still very cold. So if I left it in one place in the glass, it would freeze the glass, and the glass would probably break. So cold it is. So it's pretty cold. Now, if you watch dry ice, it does something very neat. You see it on my hand there. Now watch carefully. Just going to rub it, and it's going to disappear into a tiny bit of cloud. You guys can see. Okay, now, I know you guys can't see this closely, but there is no moisture on my hand now. There's no water there. Dry ice is called dry ice because it's not wet. It doesn't have a liquid phase. Carbon dioxide, when you freeze it, doesn't go through a liquid phase and into a solid, just goes straight from a gas to a solid. And when you melt it or evaporate it, it doesn't melt into a liquid, it evaporates straight back into a gas. Okay. So that's the neat thing about carbon dioxide. Right there. All right, so we saw the balloon condense, the air inside it and the balloon itself, and then we saw it expand when it got warm again. So if we take that expansion, now the balloon had somewhere to go because it was filled up with air first. When it shrank down, it had somewhere to go back to. But if we take that expansion and cap it off into a closed-off bottle, what do you think will happen? It'll freeze the bottle, yeah. But then as that liquid tries to expand back into a gas, what do you think is going to happen? Let's find out. We're going to cap it off here.
This didn't work.
So, what's happening inside here? Does anybody know? It's freezing the bottom of the bottle, but inside there, the liquid that's inside, what's it doing? It's trying to escape, right. The liquid, because it's so warm inside the bottle and the air out here, the liquid's trying to evaporate back into a gas. And when it does that, it needs more space. It needs more space than what the container has. Gas takes up a lot more space than a liquid, about 600 times more space. Yeah, you see it all smoking on the bottom. So as long as there is liquid inside the tube here, when we cap it off, it evaporates into a gas, and the gas cannot be contained inside here. It's not big enough, so it pops the lid off. And as long as there's liquid inside there, it'll pop the lid off. Do you have a question?
How come you see more fog on the bottom than you don't see on the top?
That's a good question. How come you see more of the cloud, the fog on the bottom than the top? Well, we touched on that earlier. Do you remember?
Because fog goes down because it's colder.
Right, cold goes down. Right. Now, some of it will escape to the top, especially if you blow in it. You see it come out the top like that because you're adding warm air into the top. But mainly the cold wants to go down, so it just falls down like that.
But how does it escape?
How is it escaping? Yeah, it's escaping through the bottom because air can get through something like this little plastic right here. Yeah, it's not completely airtight. It's airtight enough to make that happen. Yeah, thank you. It's airtight enough to let the gas build up and pop out, but not quite enough to keep all of the gas in the bottom down there. Yeah, it's still like that. Yeah, and you can see how cold it made the bottle over here. Right, that'll stay for a while. Yeah, it's very frosty. Right. Okay, so now we've been talking about how cold this stuff is and how it's sometimes dangerous, and we wear safety goggles for fun. Well, we don't wear gloves because we don't want to get trapped inside. But what happens if some of this does get on you? Like we were to splash a soup full of this on somebody. You think it would freeze you? Yeah. Does anybody else think something different might happen, or we just think it'll freeze you? Probably burn you? You think it'll burn you? Yeah. Is somebody brave enough to try it? Do you want to try it? You sure? Come stand right over here. Stand on the front. With me. We'll glad you can't, but that's all right. Okay. So what's your name? Ethan? Okay, Ethan is brave enough to let us test this on him. I was good myself. That's why I asked for volunteers. So what you're going to do, pull your sleeve up. There's yeah, up there like that. And you're just going to hold your hand out just like this, okay? Just like that, good. Just make sure you don't put your fingers together and don't cup your hand, just keep it out just like that. Perfect, all right, just hold it right there. So we're going to take a scoopful. We got a nice big scoopful right here. And we're going to pour it on Ethan's hand. Okay, keep your fingers out flat, just like that. All right, now we think it's going to burn him, we think it might freeze him, we think it might do any number of things to him. But are you ready to find out what it does? Okay, do you trust me that I'm not going to be bottling home to you today? Okay, that might be a mistake. Okay, so you're going to keep your hand out just like that. We're just going to pour it right on you. You know, feel how cold that is right there? Yeah, and that's just the fog right there. Are you ready? Are you ready?
Yeah.
Okay, let's go. 3, 2, 1. Like that. Now, Ethan, flex your hand for it. Is it frozen? No, it's not frozen. It's just a little cold. Yeah, not even very wet. Yeah. Not even really cold anymore, right? Yeah. Yeah, let's give him a hand. He did very good. So the question is, and you guys should know the answer to this, why didn't it hurt him? Why didn't it freeze him? Why didn't it do anything? Because it didn't stay on long enough. Right, yeah. What's our body temperature on average? You know? You forgot? Right, our body temperature? Not 64. What? That's closer. Someone said it over there, I think. 98.6. 98.6 is our average body temperature. Right, that's Fahrenheit. That's our average body temperature. So, this stuff being negative 320 degrees, and this being 98.6 degrees, there's nearly a 400-degree difference right there. So, it's just evaporates immediately, just like on the carpet. Now, we needed him to push his sleeve up because, like I said with the gloves, we didn't want any of that going up the sleeve and sticking up there. So we pushed the sleeve up so it can all just fall right off something like that. It evaporates immediately. It's perfectly okay. Now, again, if I had took his pen and just stuck it in there and held it in there for a while, that would be bad.